Welcome to this lecture on data manipulation in physics, where we will focus on cleaning, filtering, and transforming scientific data. This session introduces the standard workflow for turning raw data into a reliable format suitable for analysis and interpretation. By the end of this lecture, you should understand why scientific data almost always requires pre-processing before it can be used. We will cover the distinctions between raw, cleaned, and processed data, and you will learn to use the Pandas library to organize and validate your physics measurements effectively. In experimental and computational physics, data rarely arrive in a ready-to-analyze state. You will frequently encounter missing entries, inconsistent units, or sensor artifacts that must be handled. A core tenet of this work is reproducibility. We must document our transformation steps rather than relying on manual, undocumented changes. This table defines the standard terms we use for the data lifecycle. A key principle is that we perform these manipulations to make the data usable without losing its underlying physical meaning. We should never remove data points simply because they appear inconvenient. To perform these tasks, we will rely on the core scientific Python stack. We use NumPy for numerical operations, Pandas for working with tabular data, and Matplotlib for creating visualizations. Let us consider our first worked example, a simple motion experiment. The data set includes time, position, and temperature readings, but it contains a missing position value and a suspicious temperature spike that we need to address. Here, we represent the raw experimental data as a Pandas data frame. Notice the missing value at the 2.5 second mark and the sensor spike at 3.5 seconds, which are common issues in real-world measurements. Before diving into calculations, we must perform a basic inspection. We check the shape of the data, the column names, the data types, and the count of missing values to ensure we have a clear view of what we are working with. The output confirms our inspection. We have a data frame with 10 rows and 4 columns. It also identifies the missing entry in the position column, which we will need to handle before proceeding to analysis. To get a quick overview of the numerical data, we use the describe method. This provides summary statistics like the mean, standard deviation, and range, which are essential for identifying outliers or physically impossible values. Looking at the summary, we see that the maximum temperature is 99 degrees Celsius. This is an important diagnostic step. While not impossible, it is suspicious given our expected room temperature conditions and the other readings in the set. It is crucial to be careful when encountering such values. Instead of simply deleting the 99-degree reading, we will flag it as suspicious, allowing us to maintain the integrity of our dataset for further investigation. In our cleaning workflow, we create a copy of the original data to preserve it, add a flag for the temperature issue, and drop rows with missing positions. We only remove the missing position data because our upcoming velocity calculation specifically requires that column. This cleaned data frame now includes the temperature_flag column. This explicit flag approach makes our cleaning process transparent and reproducible, which is much better practice than manual editing. We can now easily isolate and inspect the flagged row. By using the Boolean mask, we can quickly retrieve and verify the specific data point causing the temperature sensor spike. The output confirms our check. Exactly one row has been flagged as suspicious. This simple verification helps ensure that our cleaning logic has worked as intended. Displaying the flagged row shows us exactly which measurement was affected. Having the comment alongside the data point helps us understand that this was indeed a sensor error. Now that the data is cleaned, we proceed to filtering. Filtering allows us to focus on the specific time range relevant to our analysis, while excluding the problematic temperature spike we identified earlier. The resulting data frame is smaller and more focused. By applying these specific conditions, we have prepared a clean subset of our data for the next phase of the investigation. Always remember that filtering is a deliberate scientific decision. It should always be driven by the specific question you are trying to answer, rather than just being a series of arbitrary programming commands. With our filtered data, we can now compute derived quantities. We estimate the velocity by calculating the gradient of the position with respect to time, which also allows us to derive the kinetic energy per unit mass. This updated data frame now includes our derived columns. These columns represent the physical quantities we are actually interested in, computed directly from the cleaned measurements. Now, we visualize the position data. This plot allows us to visually inspect the motion and ensure that the cleaning and filtering steps have resulted in a sensible representation of the experiment. The plot shows a smooth, non-linear increase in position over time. This visual validation is a critical step in ensuring that our data manipulation workflow has not corrupted the underlying physical signal. Next, we plot the derived velocity to see how the object is moving. This provides a direct look at the dynamics of the experiment based on our processed data. The plot confirms that the velocity is increasing over time. This indicates accelerated motion, which is consistent with our visual observations of the position data. This non-linear increase in position and the rising velocity give us confidence in our physical interpretation. We have successfully moved from raw, messy data to a validated set that is now ready for more sophisticated curve fitting if needed. It is helpful to understand the difference between NumPy arrays and Pandas data frames. NumPy is excellent for pure numerical crunching, while data frames are much more readable for mixed data types and named columns. As this output shows, converting to a NumPy array strips away the labels. While efficient, this demonstrates why keeping our data in a data frame is usually safer during the manipulation phase where context matters. The key takeaway is that with data frames, the column names keep our labels explicit. With NumPy, we have to keep track of the index, which is prone to error in larger, more complex datasets. Let us apply this workflow to a second example, this time involving simulation energy data. This type of structured log is very common in molecular dynamics and other computational physics simulations. The output displays our simulated energy log. We have columns for simulation steps and various energy types, which we will now process to isolate the steady-state behavior. A common requirement in simulations is to filter out the early transient period. By keeping only the steps where the simulation has reached an equilibrated state, we ensure our analysis reflects the steady-state physics. This check confirms that our filtering has reduced the dataset from 13 rows to 9. This helps us verify that we are focusing on the equilibrated portion of the simulation. The resulting data frame shows only the data points from step 400 onwards. We can now proceed with the analysis of this more representative subset of the simulation. To validate our filtering, we visualize the temperature over time. Comparing the full dataset against the filtered equilibrated subset gives us a clear look at where the transient behavior ends. The plot shows how the simulation temperature transitions and eventually settles. The markers distinguish the filtered section, clearly showing that we have successfully isolated the equilibrated steps. Finally, we can analyze the relationship between variables, such as plotting potential energy versus temperature. This kind of physical correlation is exactly what we perform the cleaning and filtering steps to achieve. The scatter plot reveals a clear trend between potential energy and temperature in the equilibrated data. This visual result is the payoff for all the careful data manipulation steps we have followed. To ensure our code is robust, we should include automated data quality checks. These functions help us catch common errors, like missing columns, early on before they lead to incorrect physical conclusions. The output here confirms that all required columns are present in our simulation data frame. This kind of programmatic verification is a hallmark of professional, reproducible research. These basic data checks help us monitor the state of our data after each major step. By checking for missing values and examining the physical ranges of our energy and temperature columns, we ensure the data remains sensible. The output shows us exactly how many rows we have and the range of values for our energy and temperature fields. This information confirms that the data is within physically plausible bounds. For a truly reproducible workflow, we must save our processed results. This allows us to share or reload the cleaned data for future analysis without having to rerun the entire cleaning script from scratch. The output shows that our processed simulation data has been successfully saved to a file. We can verify this by reading it back, confirming the integrity of the saved data. Reading the file back results in the same structured data frame we had before saving. This confirms that our saving and loading process is lossless and reliable. For today's guided practice, you will work through these 4 tasks to further explore filtering and analysis. These exercises will help you practice selecting specific data conditions and interpreting the physical results. The output for the guided practice shows how filtering by temperature allows us to isolate specific states. Notice that this task involves calculating a specific mean value for those filtered rows. The resulting table for the guided practice displays the simulation steps where the temperature exceeded our threshold. This allows for quick, targeted examination of those specific states. We can also visualize the total energy for these specific conditions. This further illustrates how filtering and plotting can help uncover physical relationships in your simulated data. The plot clearly shows the total energy behavior across the filtered simulation steps. This trend is exactly the kind of result we need to interpret the stability of the simulation. In our discussion, we differentiate between filtering by time step and filtering by temperature. The former isolates a simulation phase, while the latter selects states based on physical conditions. And it is important to know which question you are answering. To summarize, we have followed a standard workflow: preserve raw data, inspect, identify issues, filter meaningfully, derive new quantities, visualize, and validate. In the next part, we will apply these same techniques to more complex, structured, scientific text formats.